Hi guys, this is Mrs. Allison. This is day 2 of u-substitution. So what I would like you to do is hit pause, try the warm-up, and then come back. All right, so this is an example of u-substitution, but it does require us to do a little bit of manipulation first. So the first thing I'm going to do is just rewrite this as the integral of sine of x over cosine of x dx. Okay, and so there may not be a true inside function here, but think about what we could use or which part might be more complicated. And I think it might be easier to let u be cosine of x. And therefore, when I take the derivative of both sides, we get du dx equals negative sine of x. Or if I write it in the differential form, we would get du equals negative sine of x dx. So I am going to let this be my substitution in. So actually I'm going to change it to negative du. Sorry, let's do negative du equals sine of x dx. That matches. Didn't leave myself much room. Okay, so what we have then, if I rewrite this problem, is I would have negative the integral of u, 1 over u, du. Okay, well, if you remember from our derivatives, we know that the integral of 1 over u is the natural log of the absolute value of u plus c. So we would have negative natural log of cosine of x plus c. Now, sometimes we don't like to see a negative there, although this answer is not wrong. This is the correct answer. However, if you remember our properties of natural logs, that negative could actually be brought up to the argument. So it would be the natural log of the absolute value of cosine of x raised to the negative 1, which is better written as, I think I'm going to run out of room, the natural log of the absolute value of secant of x plus c. No, there's a plus c there, but this would be another answer to that same integral problem. Okay, so let's take a look at some more challenging u-substitution problems, maybe requiring us to remember a few more details. For example, let's look at this next one that actually will go back to the warm-up that we just did. So take a second and try it if you would like, and then come back and see how you did. Okay, in this problem, I am going to let u represent this x cubed plus 1. So let's go back and write that. So we're going to let u equal x cubed plus 1. And then I'm going to take the derivative of that, and I'm going to get du dx equals 3x squared. And simplifying that, I get du equals 3x squared dx. Okay, well, here's the problem, is that in here, in this problem, I see a 5x squared. So to counteract that, I am going to multiply all of this by 5/3. Oops, I'm a little too close to the edge of my screen here. Okay, multiplying the whole thing by 5/3, we get 5/3 du equals 5x squared dx. Okay, so now this looks more like what we had before. So if I go into and look at my problem, I have a 5x squared and I have a dx. So replacing all of this, I'm going to go replace this, and I would have the integral of, let's bring that 5/3 out actually. Let's do 5/3 times the integral of tangent of u du. Okay, Now I can integrate this. Well, we just looked at the integral of tangent of u, so I don't have to go through u substitution again. I can use the ideas that I just came up with about what it means to take the integral of tangent of u. And so what I would have, and let's keep it in the positive, let's do 5/3 the integral of tangent. Let's do the natural log of the absolute value of secant of u plus c. Now let's replace what u represents. So we have 5/3 natural log of the secant of u, which was x cubed plus 1 plus c. All right, you ready to try another one that's very similar? So hit pause and, well, first try number 2 and hit pause to see if you can get it before we try it. All right, hopefully when looking at this problem, you decided to let u be this inside function of 3 minus tangent of 4t. So let's let u equal 3 minus the tangent of 4t. And that 4t is in parentheses. And then let's take the derivative of this with respect to t. So du dt equals negative secant squared 4t times 4. We can't lose the chain rule. So rewriting this a little bit, we get du equals negative 4 secant squared 4t dt. Okay, so now we need to rewrite this. And if you notice in my problem that I can't quite, it needs to equal secant squared of 4t dt. So let's change that just a little bit by multiplying both sides by negative 1/4. So we would get negative 1/4 du equals negative 4 secant squared 4t dt. Okay, so now we have this integral that we can rewrite. And so we can rewrite it to say, let's do the 1/4. So let's do negative 1/4. That's part of that u. Negative 1/4 times the integral of, and in this case, all I have left is u to the 3rd power, and then du. And now I can take the integral of this. This one is actually quite an easy integral, quite easy to do the integration. So we've got 1/4 of u to the 4th divided by 4 plus c. So we get negative 1/16. Let's go ahead and plug in u. And u is 3 minus the tangent of 4t to the 4th plus c. And there would be my antiderivative of this. Okay, so let's try some that are just a little bit different, maybe a little bit more fun. All right, so looking at this, what do you suppose we should let u be? Hopefully looking at this, you see that the inside function is this x ln of x, or x minus ln of x, rather. So if we let u equal x minus the natural log of x, and then when we take the derivative of u with respect to x, we would get 1 minus 1 over x. Hey, that looks like something we might be able to use. So simplifying this, just so it's in the differential form, we'd get 1 minus 1 over x dx. And what we can see here is that this 1 minus x dx can be replaced up here with the 1 minus 1 over x dx. So again, really this problem becomes simple, just looks pretty nasty to begin with. Okay, so we would have the integral of the cosine of u du. And then when I go to take the integral of this, the integral of cosine of u is sine of u plus c, and replacing the u we get sine of x minus natural log of x plus c. So it looks bad, but really is not too bad. Okay, the last one that I want to look at is a bit trickier and is going to require a bit more work. Truthfully, I wish I had left a little bit more room on these notes because there's not quite enough in this spot. So I apologize in advance. I will try to squish in what I can. Okay, now you'll notice this one's a little bit trickier. So I can tell you that the inside function, the function that we are going to look at here, that we're going to let be u, be this 1 plus x. So I'm going to let u equal 1 plus x. Okay, so taking the derivative of both sides, we get du dx equals 1, which means du equals dx. Here's the problem. I don't have anything at the moment to deal with this x. I also don't have a way algebraically to get this expression in any way simplified, meaning I can't raise this to the 1/2 power and distribute it and try to combine like terms. There's nothing I can do here. So since I can't use traditional integration, and because right now my u-substitution is kind of failing me, what I'm going to need to do is I'm going to need to rewrite x in terms of u. Because I need to take the integral of this, I need to be able to have everything in terms of u. So let's rewrite x in terms of u. So if we let u equal 1 plus x, then doesn't it hold that x equals u minus 1? So I can make a substitution in place of x with u minus 1. So here's what that looks like. I would be taking the integral, and in place of x, I'm going to write the u minus 1 of u minus 1 times the square root of u, because that's what we let u be. And then I do have what dx is, and that is du. So now my entire problem is written in terms of u's. So I am taking the antiderivative in terms of u's. Now this doesn't really look that much better at the moment, but it can be, because this one I can simplify just a little bit more. So I'm going to rewrite this as u minus 1 times u to the 1/2 du, which means it's the integral of u to the 3/2 minus u to the 1/2 du. And when I go and take the integral of this, I'm going to go up a degree. So I would have u to the 5/2 over 5/2. Oops, that's a minus. Minus u to the 3/2 up a degree over 3/2 plus c. Now substituting back in for my u and doing a little bit of rearranging, I would get 2/5 u is 1 plus x to the 5/2 minus 2/3 u to the, u, which is 1 plus x to the 3/2 plus c. So a little bit trickier, but we just have to use and be able to rewrite our problem, our x, in terms of the u expression. Okay, let's look at just a couple others. Okay, if you recall, the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. Remember, it's the absolute value because the domain of the natural log, it really only goes from 0 to infinity. Numbers greater than 0 to infinity. And whereas 1 over x, the domain is all real numbers except 0. So to accommodate for that all real numbers, we're going to put the argument of the natural log in absolute value. Okay, so when we're dealing with the natural log function, in this problem, I am going to let my u, and I can use u-substitution here as well, I am going to let my u be this 5x plus 4. So if I let u equal 5x plus 4 and I take the derivative, we get du dx equals 5. So du equals 5 dx. The problem is that's not really what I'm looking for. I'm looking for 3 dx. So I'm going to go and multiply this entire expression by 3/5. And so we get 3/5 du equals 3 dx. And now I can go and make a substitution in for my 3 and my dx. So in my integral, I would have 3/5 on the outside. The integral of 1 over, this would be my u du. Okay, and if you notice, the 1 over u is the natural log of the absolute value of u. So this would be, if I take the integral of this, I would get 3/5 natural log the absolute value of u plus c, but substituting back in for u, we would get 3/5 times the natural log of the absolute value of 5x plus 4 plus c. All right, hit pause and try this next example, example number 2 down here. Okay, hopefully you had a chance to try this, and looking at this problem, hopefully you let u be this 5x squared plus 4, and therefore du dx equals 10x. That's not what I want. I want 3x. So to accommodate that, I'm going to, actually, let's rewrite this. Du equals 10x dx. So now let's multiply both sides. Well, I want it to be 3, so let's multiply both sides by 3/10. So we get 3/10 du equals 3x dx. And now I have my substitution that I can substitute all this in for. So let's write that 3/10 outside. Oops, let's use the pen. So 3/10 times the integral of 1 over u du. And really, we're back to the same problem we just did, pretty much. So when I take the antiderivative of this, we get 3/10 times the natural log of the absolute value of u plus c. So we get 3/10 times the natural log of the absolute value of 5x squared plus 4 plus c. How'd you do? Okay, well, this next one's a little bit messier. So let's see if we can make any sense of it. To be honest, on this one, what I would probably do first, just for visual, is pull out the 5, because that leaves you with 1 over x natural log of x dx. And I think this might be visually easier to see. What do you think we should let u be? Well, if you said we should let u be the natural log of x, you would be correct. That is what I think we should let u be. So let's let u equal the natural log of x. Here's why I think that's important. If u is the natural log of x, what is the derivative of u with respect to x? Right, it's 1 over x. So simplifying this, we get du equals 1 over x dx. Now, why might I do that? Well, maybe let's rewrite this integral just a little bit differently. What if I call this 1 over x times 1 over natural log of x dx? Do you see this in my integrand? I see it with the 1 over x dx. And then I have my u down here in the denominator with the natural log of x. So if I were to rewrite this, the 5 we already had outside, the integral of, well, the blue part just becomes du. And so I have 1 over u du. And again, a pretty easy integral to take now that we have that opportunity to take the integral. I've written it in such a way that it makes it easy. So we have 5 times the natural log of the absolute value of u plus c, which would be 5 times the natural log of the natural log of x plus c. So while it looks worse, it's really not that much different. Okay, I'm going to caution you on number 4 just because of notation. We need to watch our notation carefully, but try number 4. Hit pause and then come back and see how you did. All right. The notation on this one is important. So I am going to rewrite this integral, and I'm going to call the numerator the natural log of y to the 2/3 power. I'm going to do to the 2/3 power because with this being a cube root, that gives me my 1/3. And with the natural log being squared, that gives me my 2. Okay, so now rewriting the denominator, that's not going to change. But I think writing it in this form makes it a little bit easier to see what we should let our u be. So let's let our u be the natural log of y. That would be my inside function. Even though it's not in the denominator, it's still my inside function. And therefore I would get du dy equals 1 over y. So du equals 1 over y dy. Now the problem is I want this to be a 4, so I'm going to multiply this in the denominator. I want it to be a 4, so I'm going to multiply this by 1/4. So I get 1/4 of du equals 1 over 4y dy. And now these look the same. And if you notice, now I have the 1 over 4y dy taken care of. Okay, so let's go back and make substitutions for all this. So I'm going to have the 1/4 outside. So let's pull that out. 1/4 of the integral of u to the 2/3 and then du. So 1/4 u to the 2/3 du. Okay, now let's integrate this. And integrating this, I'm going to get 1/4 of, well, I'm going to go up a degree. So I would get to the 5/3 over 5/3. Let's put that in big parentheses, plus c. Okay, kind of messy, so let's rewrite that. So I'd have 1/4 times 3/5 times u to the 5/3 plus c. And so I get 3/20, and u was the natural log of y to the 5/3 plus c. How do we do? So while they look different and maybe a little bit uglier, they're okay. Now the one thing I want to caution you on a problem like number 4, and I'm going to scroll up just a little bit, is how much the notation matters. Okay, when we talk about notation, notation is important. Where I don't want you to get hung up is in what this means. So for example, if I have the natural log of y to the 2/3, okay, this could be equivalent to 2/3 natural log of y using the natural log properties. Okay, so that's where those properties from log and natural log come into play. Why does this work? Well, because at this point, the 2/3 is only attached to the y. How that's different is if we have the parentheses natural log of y to the 2/3, this is not equivalent to 2/3 natural log of y. I can't use that power property here because that 2/3 applies to the whole log. We have to take the whole log to the 2/3. You would be better off writing this one as the cube root of the natural log of y squared, or like the problem had it today, the cube root of the natural log squared of y. So either of these or any of these are equivalent. Just make sure you're watching your notation. That notation really does matter. Whether it's the power to the argument of the natural log or whether it's the power of the whole natural log. So just pay attention to that as you go through. Otherwise, hopefully u-substitution is beginning to make a little bit of sense, your assignment today is that u-substitution practice worksheet, and we will see you soon.